Now let us consider high spin manganese 2 complex in an octahedral environment. So we are going to discuss the high spin Mn2 octahedral complex. Its ESR spectrum, that is how many lines, ESR lines will be there in the spectrum. So high spin manganese 2, its electronic configuration will be 3D, outermost electronic configuration will be 3d5 4s0. Five unpaired electrons are there. So before going to the details, let me tell you that from this example, you will be able to observe zero field splitting, Kramer's degeneracy, as well as nuclear hyperfine splitting. The manganese, why we are able to observe this nuclear hyperfine splitting means here the manganese nucleus, the nuclear spin quantum number of I of Mn nucleus is 5/2. And we are considering an example where the ligands are having nuclei where, with I is equal to 0. So the only nuclear spin quantum number I not equal to 0 in this example is for manganese nucleus. So let us consider the electrons first. There are 5 unpaired electrons. So the total spin of the system will be 5 into half, which is equal to 5/2, and the different spin states will be -5/2, -3/2, minus half, plus 3/2, and plus 5/2. Okay. Now, in the absence of magnetic field itself, there will be zero field splitting because of the electron-electron interaction. There are 5 electrons. So, in the absence of magnetic field itself, different spin states split into various energy levels. Plus or minus half, plus or minus 3/2, plus or minus 5/2. Like these 3 different energy levels exist. So that is called zero field splitting. And you can see that in each of the energy level, 2 spin states exist. In this energy level, plus half as well as minus half spin states are there. In this energy level, plus 3/2 and minus 3/2 energy levels spin states are there. In this energy level, plus 5/2 and minus 5/2 spin states are there. So, here you can observe Kramer's degeneracy. Each energy level is doubly degenerate in the absence of magnetic field. So that is Kramer's degeneracy. Now what happens when you apply magnetic field? The degeneracy of each level is lost. So you can see that different spin states now are having different energy levels. minus 5 by 2, minus 3 by 2, minus half, plus 3 by 2, plus 5 by 2. 6 different energy levels with 6 different spin states. Now, so if there is no nuclear hyperfine splitting, there will be 5 transitions. Obeying the spectroscopic selection rule, delta ms is equal to plus or minus 1. But here, manganese nucleus is having the nuclear spin quantum number 5 by 2. Nuclear spin quantum number of manganese nucleus is 5 by 2. So, that will result in the splitting of each electronic spin state into 2i plus 1 energy levels. That will be 2 into I of manganese is 5 by 2. So, 2 into 5 by 2 plus 1, which is equal to 6. And what are those spin states? That is Mi is equal to minus, that's minus I2 plus I. So, minus 5 by 2, minus 3 by 2, minus half, plus 3 by 2 and plus 5 by 2. Okay, so here you have to keep in mind that each MS level split up into 2i plus 1 spin states with having Mi is equal to minus 5 by 2 to plus 5 by 2. So here we will take this one, this ms is equal to minus 5 by 2. That will split up into 6 spin states. Okay. Now, what are their values? Here the lower energy will be plus 5 by 2, plus 3 by 2, plus half, minus 3 by 2, minus 5 by 2. Okay, so here you can refer to the hydrogen atom example where we have seen that how the nucleus affects the electronic spin transitions. So where ms is having negative value, Mi will be having positive value as the lowest energy. So here also this minus 3 by 2 spin state split up into plus 5 by 2, plus 3 by 2, plus half, minus 3 by 2, minus 5 by 2. For each state you have to write like that. I will write one more example for this because here the space restriction you can work out. One more example here where ms is equal to plus 5 by 2. So in this ms is equal to plus 5 by 2 also there will be 6 states, 6 spin states. Here the lowest energy will be minus 5 by 2, minus 3 by 2, then minus half, then plus half, then plus 3 by 2, then plus 5 by 2. Okay. One more example I will work out. For plus 3 by 2, it will be minus 5 by 2, minus 3 by 2, minus half, plus 3 by 2, plus 5 by 2. Here in the negative value, so ms is equal to minus half. I will take one more example so that you will understand. It will be plus 5 by 2, plus 3 by 2, plus half, minus 3 by 2, minus 5 by 2. So for all the levels you have to write like that. Here you have to write for ms is equal to plus half, these splitting up into 6 spin states, and this minus 3 by 2 again splitting into 6 spin states. Okay. I have worked out only the four spin states only. Okay. So now how many transitions will be there? You have to keep in mind that the spectroscopic selection rule is delta ms is equal to plus or minus 1 and delta mi is equal to 0. So keeping in mind that, you can do that, and you will observe that there will be, here already there are 5 ms states, 2 ms states, 1, 2, 3, 4, 5, 6. Okay. So which corresponds to 5 transitions. So there will be 5 into, each ms splits up into 6 spin state. So 5 into 6, you will be able to, we can predict that it is expected that there will be 5 into 6, 30 ESR lines in the spectrum. So here you can see that zero field splitting exists, Kramer's degeneracy is there, and again nuclear hyperfine splitting is there, which gives rise to 30 ESR lines. Thank you.